In my introductory video on YouTube about tides, I talked about the fact that in times gone by, people could look at the moon and see what the tide was going to be doing in their local area. They'd know all about it and they'd know from generations past. Well, we can still do that, as I mentioned. I do it myself around here. I hardly need tide tables, quite honestly. I can look at the moon and see what's going to happen. But if I really need to know down to the nitty-gritty, to the nearest half a metre or something, what the tide's height's going to be, I've really got to use the tables. So we're going to get onto that in a minute, but before we do, we need to understand the definitions which the tide revolves around. There are a number of definitions involved in tidal height calculations, but there are two which are, well, particularly easy to understand. There's no numbers involved at all in this. We just have to understand what's going on. And the tide is essentially being pulled by the gravity of the moon as the Earth turns under the moon. The moon goes round the Earth once in a month, which is why the tide advances every day. But the Earth is turning under the moon. As it does, it drags the tide with it. The sun is also exerting a gravitational influence, because if it wasn't, we wouldn't be going round the sun, we'd be shooting off into interstellar space somewhere. So the sun's working at it as well. When the sun and moon work together, then we get a big tide, because the gravity is additive. When they're working against one another, we get a much smaller tide. And here's how it is. When the sun is shining full on the face of the moon and we get a full moon sailing through the clouds, then we have a big tide. They're in line. And when the sun is shining behind the moon so that we can hardly see the moon at all, maybe just a tiny little crescent of a new moon as the moon sets invisibly behind the sun, then they're in line again and we get a big tide. Now the French have a name for this. These big tides, they call them vive eau, which means living water. Our term is rubbish, really. I don't know why we've got this term, but they're called spring tides. It's very nice, it sounds good, but it doesn't mean anything to do with the seasons of the year. And people imagine that a spring tide comes at April. Well, you get one in April, you get two in April actually, and you get two in every month. So nothing to do with spring, but it is called a spring tide when everything's lined up and you've got a big tide. When the moon is out to one side of the Earth, so the sun's shining from over here, the moon's over there, you see a half moon, either waxing or waning. Doesn't matter which, because the sun and the moon are pulling against each other and the tide will be relatively small as a result. It's about half the size actually, it moves about half of the amount of water, and the French call it morte eau, dead water. As for us, we call it a neap tide, N-E-A-P, neap, and that's it. So we got 2 spring tides a month and 2 neap tides a month. You'll see how important these are when we get on to looking at the tables, but for right now, that's enough. We're going to go inside now and I'm going to put down a plan, a piece of paper which shows what tide is what and what part of the tide we're interested in. In other words, we're going to get down to the definitions. And don't forget, you've got to crack these definitions because you go on. If you try and start at, as it were, page 5, you'll be hopelessly lost. You might as well not have started at all. Crack the definitions first and then you'll know what questions to ask. Right, off we go. Okay, we're back inside now to talk about tidal definitions, the bedrock of the whole thing. But actually, everything to do with tide is about height of water. It's about how high the water has climbed when pulled by the moon. But it has to climb from some starting point, doesn't it? There's got to be some datum whereby everything else is built on it. And what the tidal calculations and heights are built on is chart datum. And chart datum is the soundings that you actually see on the chart. Here's a bit of chart, and like every bit of chart you've ever seen, it's covered in soundings all over the place. And these soundings are taken at a certain point of the tide, aren't they? Because the tide's going up and down. Somebody's had to make a decision sometime about how this is all going to work. Well, here in Britain and France and a number of other countries that have big tides, it's actually very, very simple. Chart datum is lowest astronomical tide. That is, the lowest the tide can ever be when it's being pulled by the moon and the sun. There are extraneous factors on the tide, such as which way the wind's blowing, how hard it's blowing, where from, what the atmospheric pressure is, and odd things like that. But the one thing that is utterly predictable is where it's going to be in relation to the sun and the moon. And that is the astronomically predicted tide. So chart datum in Great Britain and surrounding countries is lowest astronomical tide. This is a good thing, because what it means is that what you see on the chart is the very worst case scenario of what you're going to get. Very, very occasionally it might get lower than that for various reasons, but to all practical purposes you can more or less forget that. And if your boat draws 2 metres and it says on the chart that there's 2.5 metres and it's a nice calm day, it means you can probably creep in. So that's worth knowing, isn't it? Some places it's not as simple as this. In North America they have a different system, and I'm not going to go into that because their system seems to me to be quite complicated. I've written a couple of textbooks for American sailors, and I must say that I find the tidal height calculations complicated compared with ours over here. And their tides, generally speaking, not everywhere, but generally speaking, are smaller than ours, and it's less of an issue really. In the Baltic Sea, where there's no tide at all, I think the Swedish charts, I believe, are worked on mean level. That is probably the average sea level that you're likely to get, and so on. But never mind all that. What we're interested in is what happens in Britain. Lowest astronomical tide. That is chart datum. So that's where we start from. Okay, now let's put the picture up and have a look at the definitions that we're going to build everything else on top of. Here we go. Okay, we're on my computer screen now. We've got the Pride of Baltimore thundering along on the port tack. We'll get rid of her and pull up the picture we want, which is the tidal height definitions. Right, off we go. Right down at the bottom here we've got lowest astronomical tide, chart datum. That's it, that's what the chart's built on, and below the chart datum are all the chart depths, because all the depths you see on the chart are measured below chart datum, except for drying heights. And in tidal waters you will find there are certain areas of the chart in a different colour. They're generally green on Admiralty charts, but it does vary, and those depths are above lowest astronomical tide, which means that when the tide's very low, that particular little bit of seabed will be exposed, it'll be dry, and it's called a drying height. And it appears on the chart with a single line underneath the sounding to tell you that it's a drying height. So there it is. A lot of the time the drying heights will be covered. This particular one is even covered at low water springs. And here's low water springs sitting up above chart datum, so that on an average low water spring, a mean low water spring, you'll find that there will be a height, a tidal height, and a height is the height of tide above chart datum. That's what it's called, and here it is, height of tide. This particular height of tide is going up to sea level, and it's an arbitrary figure which I've just pulled out of my head, could be anything. But all of these are heights of tide. So we've got low water springs is the lowest one of them. Low water neaps is above it, because low water neaps, of course, is going to be less extreme than low water springs. Forget mean level for a moment. We'll go up again and we'll get high water neaps, which is lower than high water springs. And here's an important point. The difference between high water and low water on any given tide is called the range of that tide, the range of the tide. So here we have the spring range between low water springs and high water springs, and here we've got the neap range between low water neaps and high water neaps. The mean level is not something that actually we have to bother about very much. It doesn't appear in tidal height calculations very often at all, and it's, if you like, the average sea level. It has some value in some places, but we don't use it very much in home waters over here. Now then, what about the heights of things that are standing up above the water all the time, like a lighthouse or a big rock that's sticking up a stack, perhaps with a height written against it on the chart? And a lighthouse will have a height written against it, the height to the lantern, above. But above what? Is it above chart datum? Well, no, it's not. It's above mean high water springs. It's above the average of all the high water springs that you're ever likely to get, and that's what it's measured above. So if you want to know the exact height of something at any given time, you'll have to do a calculation for the tide and find out how much the tide is lying below mean high water springs, or it might be at mean high water springs. It could even be above it if it's a big tide. And so we come on to the last one, which is the vertical clearance for a bridge, or for an overhead power cable perhaps, or even something else, I don't know, but those are the two main ones. And they are given now on British charts very sensibly above the highest astronomical tide. The highest astronomical tide is, if you like, the opposite of the lowest astronomical tide on which chart datum is based. The highest astronomical tide is as high as it's ever going to get. And it's as high as it can be predicted using only astronomical phenomena. It might get a little bit higher if the pressure's very low, and we'll go into that later, but the highest it's ever going to be by normal prediction. And that's really sensible, because it means if it says there's 40 metres clearance on that bridge, that's what there's going to be. Good. Now that we've sorted out the tidal definitions, we can move on to something solid and get hold of some actual figures for the day. And we're going to open the 2020 copy of Reed's Nautical Almanac to find our information. All the tide tables are in there and all the information we need to be able to work out what's happening between high and low water. I wouldn't go to sea without Reed's myself. This is not an advert for Reed's, it's just simply the statement of what's happened to me over a lifetime of sailing in home waters and foreign. In home waters, all the information you're ever going to need is in there. There's some basic pilotage information. You need a pilot book as well to back it up. But for what we're interested in right now, the tidal information is the thing. Reed's produce effectively what is more or less a copy of the Admiralty Tide Tables. The Admiralty Tide Tables is yet another book to buy, and you don't really need to buy it because it's all in Reed's. It's just slightly smaller in Reed's than it is in the ATT, but apart from that, it's the same thing. It's the best information that it's available, and it's very accessible. So here we go. I'm going to open the book and let's see what's inside. We're going to the port of Liverpool because it's the nearest salt water to where I grew up. Okay, well, I've opened my Reed's Almanac at the page for the port of Liverpool in the autumn, and I've made a little box around October the 16th because that's a useful day. We might as well use that day for our sums. So if we look closely, we can see that low water is given at 0502 and it's 0.7 metres. Well, don't forget that's 0.7 metres above chart datum, LAT, lowest astronomical tide, so that if the chart reads 3 metres, the actual depth of water at low water around Liverpool is going to be 3.7 metres. At high water, at 10:25, it's 9.7 metres has come up. That's a big tide, isn't it? So we've got 9.7 metres above chart datum, so that's got to be added to our 3 metres of a sounding, which gives us 12.7 metres. Now then, look, the difference between high water and low water is 9 metres, isn't it? 0.7 from 9.7 is 9. So that's the range of the tide. And that's the information we're going to want as we move on. In a little while, we're going to have a look at how to calculate how much water's up between low water and high water and what time it's going to be. But first, there's one more thing we have to check. This little box here, which is always here on the page, tells us that it's standard time. The times given here are UT for this standard port. UT is the same as Greenwich Mean Time, and it's the basic time that we work to. In summer, of course, we add an hour in Britain to give us longer evenings to sit outside in the pub. Now then, it tells us here that for summertime, we must add 1 hour in a non-shaded area. There's shading over here. We're in the non-shaded area, so we're still on summertime, and we're going to add an hour to these times if we want the time to coincide with our watch. So low water is going to be 0602 and high water is going to be 1125 on our watch. Right, now let's carry that information over. We're going to zoom out on the so we can see both pages, and we're going to do something with that information so that we can find out exactly what the tide's doing between low water and high water. And you'll be delighted by this. It's surprisingly easy. Right, we've zoomed out so we can see the whole of the page. This is what it looks like. We've got the numbers on the left, and if we flip over one page on the left-hand side of that, we're going to get the numbers for the rest of the year. But notice that on the right-hand page, there is a graph. That is the secret weapon for finding out what's going on between high and low water. And we're going to go into that now and see what happens. We zoom in on it. That's what it looks like. Okay, now what we're looking at here is what's called a tidal height curve. This gives us all the information we need to find out what the tide is doing between high and low water. And to use it, we proceed as follows. First of all, we note down the height of low water down here. Look, low water heights in meters. And our low water height was 0.7. These are big tides, so that's 1 metre. That will be 0.8, so 0.7 will be there. And high water, we note down the height of high water, which was 9.7, which is going to be there. Now then, we get a useful ruler. We've all got one of them kicking around in the chart table. And we use the ruler to flatten out the page, because being a book, it's always going to wander around a bit, be a little bit roly-poly. So we flatten our page out and we join those two dots with a nice bold line like that. Now, we write down the time of high water in the little box at the bottom, and it's 10:25. There it is. Rotten writing, never mind, I can read it, and I'm the navigator. Now then, suppose we want to know how much water will have come up 3 hours before high water. Well, this is what we do. The hours are noted along the bottom here, and we look high water -1, -2, -3. So there's 3 hours before high water. We put our ruler on there, and we just go up the line like that until we cut the curve of the graph. Then we put the ruler across from the point at which the line is being cut, and we construct a line across like so till we cut our, this is what I call the line of the day. We're going to cut the line of the day there, and then we're going to draw another line up to the top of the box from here, like so. And there's our answer. The answer is 4.8 metres. Here's 5, 4.8 metres. Simple as that. It couldn't be easier, really, could it? There are other ways of doing this, but I think this is the favourite, really. It just is so easy to do. And when I start out on a day's trip and I'm going to be in tidal water, first thing I do is just fill in one of these curves, so that at any time, if I want to know how much water's up, I can just refer to this. Well, let's say it was 2 hours, and let's say it was 4 hours before high water, 4.5 hours. There we are, we're on this line here. So we go up to the line. Now this is interesting because you notice there are two lines here. There's a thick line and a pecked line. Well, the thick line is for the mean spring tide, and the pecked line is for a neap tide. Sometimes these are very different. Here in Liverpool they're not, just a little bit at the start of the flood they're different. And we know we're on a big tide here because we're actually beyond mean low water springs. Look, there's less water up than there is at mean low water springs, and there's more water up than at mean high water springs. So we just join our line like that, and we can, this time we don't need go up, we can drop down because it's not so far to go, is it? And there's our answer, 1 metre. Couldn't be easier, could it? That's all you do. And if you want to know at what time, for example, there would be, let's say we've got to cross a bar and we need 2.5 meters of tide up to do it. Well, you do it the other way around. You start at 2.5 meters, which is halfway between these two here. We drop a line perpendicular down to the tide line. There it goes. We come across from the point at which it's cut the line to our spring tide line. And then we drop it down into the time boxes. And lo and behold, the answer is, well, my line's not quite straight. That's what happens when you're trying to draw. I can tell you, it's not easy doing this in front of a camera. I'm trying to squirm around a tripod here, but the answer is 4 hours, not quite 4 hours, is it? We've got 2 hours, 3 hours, and we're just a bit short of 4 hours there. We're probably 5 or 10 minutes short of 4 hours before high water. And that's it. That's all there is to it for working the tidal curves. Not bad, is it? If you don't like graphs and you're navigating in an area where the tide really behaves itself and goes up and down in a nice even wave like a sine wave, then there's another way of doing this, and it just involves very simple numbers, sort of schoolboy mathematics. And this is what you do. First of all, you find the range of the tide. Remember that one of the definitions? And the range of the tide is the difference between high and low water. So if you subtract low water from high water, you've got it. And then, with the range in hand, you apply the following little formula: 1, 2, 3, 3, 2, 1. And what does that mean? Well, each of those numbers represents a 1/12 of the range of the tide. So you divide the range by 12, that gives you 1/12, which is the magic number. And in the first hour, 1/12 of the tide will come up. In hour 4, 9/12 will be up. That's 1 plus 2 plus 3 plus 3. And in hour 5, 11/12 will be up, and so on. That's how it works. It's interesting because it shows you actually how fast the tide's rising and falling, and it barrels up in the 2 middle hours. Hours 2 and 4, it's a lot slower, and hours 1 and 5, it's just trickling out and in, really. That's the end of it. So let's look at an example. Let's say we've got a low water height of 0.4 meters, and it's at 12:15. We've got that from the tide tables, and high water's at 18:15, and it's 5.2 meters. The range of our tide is 4.8 meters, 0.4 from 5.2, and 1/12 of the range, 12 into 48 goes 4 when I went to school, so that's 0.4 meters is 1/12. Now at 14:15 we'll have 3/12 of the range up. 1/12 in the first hour and 2/12 in the second, and that's 3 times 0.4, which is 1.2. To find the height of tide above chart datum, we add that figure to the low water height. So the answer is height of tide above datum is 0.4 meters plus 1.2 meters that we've just calculated, and the answer is 1.6 meters. It's as simple as that. Note that when using the graph in Reeds or the Admiralty tide tables, the answer you extract actually is the height of tide. You don't have to add low water to that. You only add low water when you're using the rule of 12ths.